Hi, this is Sungwil Lee. Thanks for having me. Also, thanks for giving me this great chance to share what I'm thinking about superradiance field. Our group at Korea University is trying to translate the idea of superradiance into a practically viable device, particularly by using DNA nanotechnology. Let's jump into it. As we all recognize, Robert Dicks suggested radical idea about superradiance in 1954. It can be simply conceptualized by a collective resonance of electric dipoles of quantum emitters, which are assembled at the subwavelength scale. As a result, we can expect the strongly boosted emission, proportional to emitter number n to n. Thus, the key to achieving superradiance is to assemble the quantum emitters in a highly controlled manner, much like the circularly organized black arrows herein. In particular, their distance needs to be deep subwavelength scale, while simultaneously each of emitter have to be regularly organized, to induce a collective and coherent interaction between them. Toward this end, several strategies for the experimental validation of superradiance concept have been suggested thus far, as summarized in this slide, including random aggregation of quantum dots, or molecular dyes, and cavity-assisted pushing of the gas-type emitters into a coherent state. These are quite good, as enough for a proof-of-concept demonstration of superradiance. However, unfortunately, these are neither deterministic or scalable, limiting the practical use of superradiance into a practically viable regime. Thus, the question becomes, can we do better, especially in making superradiance devices, to be more at the practically viable level? In this talk, I'd like to persuade you in here that it's actually possible by using DNA nanotechnology. Many of you in here Korea Physical Society meeting will not be so familiar with these beautiful molecular structures of DNA. In 1953, Francis Crick and James Watson unveiled duplex nature of DNA, which results from the complementary binding of two single-stranded DNA, as indicated in this slide. Each single-stranded DNA can be sequentially digitalized by 4 codes A, T, G, and C. Note that it can meet only with T through 2 numbers of hydrogen bonding, while C can meet only with G through 3 numbers of hydrogen bonding. Previously, Watson and Crick suggested AD and GC bindings have the same numbers of hydrogen bonding, as highlighted by their original Nature paper. Later on, it is revealed that AD and GC binding can be achieved through a different number of hydrogen bonds. This is the reason why single-stranded DNA can do some sort of complementary binding. What's the complementary binding? Basically, DNA is a polymer with 4 digits A, T, G, and C. Thus, the possibility for differently sequenced, single-stranded DNA is for to the number of bases. For example, let's say we have dealt with single-stranded DNA with 12 bases, and we can have for to 12 different numbers of single-stranded DNA. That's actually about 16 million, over the millions. Each differently sequenced, single-stranded DNA can meet only with the complementary pair, as this is the only way to minimize the Gibbs free energy, as shown on right of this slide. The complementary binding of these to DNA is the same as what happens to the chemical reaction. When to single-stranded DNA is bound, there's huge entropic compensation, resulting in an abrupt increase in Gibbs free energy. However, the continuous increase in hydrogen binding and the resultant continuous reduction in enthalpy can overcome this thermodynamically unfavorable situation. Thus, single-stranded DNA should undergo binding, unbinding, rebinding, unbinding, rebinding, until they are fully complementarily bound. Eventually, they can reach at the lowest Gibbs free energy. Overall, this complementary binding is the only way to minimize the free energy. Then, it's time to get into the detailed structural features of DNA duplex. It has a helical feature, obviously, with alternative, major, and minor grooves, and base pairs formed through hydrogen bonding are stacked in a self-aligned fashion. These stacked base pairs tend to twist along the long axis of the duplex. This is way to mitigate the possible ionic repulsion between the negatively charged bases. Meanwhile, Note that the width of the duplex is about 2.0 to 2.5 nanometers. The distance and the rotational angle between the stacked base pairs are about 0.33 to 0.34 nanometers, and about 33 to 34 degrees, respectively. Then, I should emphasize that DNA complementary binding allows us to grab molecular, or quantum dot emitters, as shown here. In this field, this complementary binding has been viewed as a binding of handle and anti-handle, much like this. Herein, these reddish or bluish dots correspond to quantum emitters. Then, the question becomes, can we put some spatial ordering of such DNA-grabbed quantum emitter? Yes, it's possible with the concept of DNA as shown in this movie. Long single-stranded DNA, with about 8,000 bases, can be folded into any desired position, with the assistance of short stapling single-stranded DNA. Finally, we can obtain the folded DNA into any desired shapes. This beautiful nano-architecturing can be done in a parallel fashion. What I meant by a parallel fashion is that many of these folded DNA nanoarchitectures can be obtained at once, particularly mixing the required DNA, heating them up, and cooling them down are enough to obtain many of DNA origami. Herein, as an example, you're showing the many smiley faces of DNA origami obtained in a single batch by putting them onto a substrate. Then, we can image them through an atomic force microscope. We can see the world's smallest happiness as like this. As shown here, more important features of this DNA origami technology can be summarized. First, sub-100 nanometers scale. Any desired shaping is possible through DNA origami. Second, its shaping resolution can reach at 2.0 or 2.5 nanometers, far beyond what the state-of-the-art semiconductor process, such as EUV photolithography, can do. Third, as I emphasized just now, it is parallel nanofabrications with which many DNA origami can be obtained at once. Finally, the surface of DNA origami can be decorated with handle single-stranded DNA. Therefore, we can deterministically position each of quantum emitters with 2.0 or 2.5 nanometers resolution. Practically, its resolution can be extended to about 5 nanometers to 8 nanometers. Anyhow, the surface of DNA origami can be digitally pixelated via the molecularly addressable position of quantum emitters, as shown in this slide. Let me briefly introduce our group's recent results toward this end. We designed and obtained this square-shaped two-dimensional DNA origami. Here, the left indicates the full atom molecular dynamics simulation of the designed DNA origami, and we can see the atomic force microscope imaged DNA origami obtained from this molecular design. It is visible that theoretical blueprint is well and deterministically materialized. On to such DNA origami molecular pabboards, we deterministically position to different molecular fluorescence dyes at each different position. By using super-resolution optical microscope imaging, so-called storm or paint, we can direct observe each different positioned, individual fluorescence dyes. Yeah, we can say that DNA origami can indeed act as a molecular pegboard for organizing quantum emitters. How about this kind of vertical alignment and assembly of quantum emitters? Toward this, we can use different kinds of DNA origami pegboards, as shown in here. What we can see here is the barrel-shaped, three-dimensional DNA origami, and each of them can be coaxially stacked. When I showed this result, I'm frequently asked, are they uniform enough for a device-quality application? Yes, as shown in bare transmission electron microscope images of corresponding DNA origami, these stuffs are really uniform, allowing us to use as a reliable and predictable model systems. So, it's time to decorate the inner and outer surfaces of such three-dimensional DNA origami molecular canvas. It has about 120 nanometers in diameter and about 250 nanometers in height. The surface can be pixelated by each different fluorescence, dye, molecules. What does it look like? Can you see the appearance of a specific iconic pattern? Yes, you can see the nano-rendered minions. Also, we need to check the uniformity of these molecular assemblies. We randomly lined up each different nano-minions, and these quantum emitter DNA, or origami, hybrids turned out to be really uniform. Furthermore, as I emphasized before, as well as molecular diquantum emitters, many other nano-optical components can be co-integrated onto DNA origami pegboards, including plasmonic gold nanoparticles, fluorescence nanodiamond, which is another important class of quantum emitter, and colloidal quantum dots. Over the last few years, we undertook a lot of efforts to assemble plasmonic gold nanoparticular cavity onto the surface of DNA origami, as shown in right panel of this slide. In more detail, gold colloids at the moment can be synthesized with unprecedented quality. For example, a long time ago, Michael Faraday recognized plasmonic resonance from gold colloids. But, at that time, gold colloids are highly polydispersed. In these days, we can synthesize much more high-qualified gold colloids, massively and cost-effectively. And we can also have a well-matured method for attaching the enough DNA anti-handle onto these gold colloids. Also, the recent advances in chemical synthesis enabled the more sophisticated nano-shaping on gold colloids, much like this gold colloids, with the exotic chiral topology. Overall, we can deterministically incorporate molecular fluorescence quantum emitters in the desired position in plasmonic cavity, for example, assembled by two spherical gold colloids and one DNA origami. Through that we can deterministically control over the coupling between molecular emitters and plasmonic cavity. It looks quite good in terms of parallel developing of spatially ordered quantum emitters. However, the paired handle anti-handle DNA duplex tend to undergo the wobbling or pivoting motions onto the surface of DNA origami. This slide shows our molecular dynamics studies onto the thermal distributions of duplex orientation, theta, of DNA duplex hanging out from the surface of DNA origami. Even with the duplex walls or forest around the target DNA duplex, it turns out that DNA duplex could undergo a distinct wobbling motions, ruining the deterministic ordering or assemblies of quantum emitters. Then the question becomes, how can we overcome this technological problem? Alternatively, we can use the mechanical inserting the target emitters into the major or minor grooves of DNA duplex within DNA origami, rather than hanging DNA handle anti-handle duplex, as shown in here. By control over the stain within the duplex, the orientation of dye molecules, for example, Psi5, can be deterministically controlled. Also, dye molecules wrapping along the surface of DNA duplex can be controlled to be assembled into J aggregate or H aggregate with respect to the salt concentration. Let us more detail how the stain of duplex within DNA origami can control the orientation of molecular emitters, such as Psi3 and Psi5. By subtracting several bases of single-stranded DNA of duplex, we can selectively stretch out the DNA. Therefore, the orientation of long axis of molecular emitters can be aligned along the direction of such DNA stretching, as shown herein. Also, as reported by Morner Group at Stanford, the molecular dye emitters can be interweaved at each base pair. Thus, we can directly visualize the helically rotated molecular emitters along the long axis of DNA duplex. Conclusively, we could become aware that DNA duplex allow us to deterministically steer the molecular emitters in a highly controlled manner. Lastly, we would like to provide our strategy for large array integration of such DNA quantum emitter hybrids. We're heading toward assembly of giant DNA origami molecular pegboard. In general, available size of each individual DNA origami is limited by the total length of single-stranded DNA called scaffold DNA. Its size is typically under 100 nanometers in lateral dimension. We believe that this size limit can be overcome by using cooperative assembly of DNA origami, as highlighted by this slide. In particular, single DNA origami with rod or tube shape can be assembled into the giant DNA origami with lateral dimension of about 500 nanometers. This can be achieved through a precise control of cooperative interaction between each DNA origami. This work is carried out through the collaboration with Professor William Shi Group at Harvard. And each individual cross-section point can act as an independent pixel for docking molecular emitters. Our final goal includes the wafer-scale integration of these giant DNA origami quantum emitter hybrids by using technology referred to as DNA origami displacement. Hopefully, we could achieve this kind of device quality, plasmonic cavity integrated quantum mechanical devices, enabling superradiance, guiding it along the any desired pathway. And we believe this grand challenge can come to the fore through the recent advance in DNA nanotechnology, what I introduced today. Lastly, I should appreciate these guys, graduate students of mine, Dr. Changwon Lee and Sunghun Park, who have hardly worked on it. And also I would like thanks Prof. William Shi at Harvard and Professor Ashwin Gopinath at MIT for allowing me to get into DNA nanotechnology and inspiring me toward this super radiance work. Thanks for your attention.